Okay, hi guys. So in this lecture, we'll be continuing on seeing examples of compounds, and we have to categorize them whether they are uh, enantiomers, diastereomers, or other compounds such as whether they are identical or some other isomers. Okay, so let us start with another example. So we have to we have to say whether this compound is whether these two compounds are enantiomers or not. Both are at equatorial, and these both are coming out of the plane. Okay, so if you have a close look on these compounds, you can actually um, say that these will not be superimposable, because if we draw if we actually rotate it along this plane to 180 degrees, so these two carbon atoms will both go down the plane. So one would be equatorial and another would be axial, right? Because two adjacent equatorial cannot be both be down at the same time, neither two axial at adjacent carbon positions be down at the same time. Okay, so for both the carbon atoms substituted groups, adjacent carbon atom substituted groups, they have to be down only when one is axial and another is equatorial in the down position. Okay, so these are diastereomers. Let us name them as 1 and 2. 1 and 2 are diastereomers. Okay, so let us look at second example, where we have this compound and this is C. There is a methyl group here, there is H here and OH here. Similarly, we have this, where we have C, OH as this, and H as this. So let us compare whether 3 and 4 are enantiomers, diastereomers, or anything else. So if we look at both of them, so obviously there is a they are geometric isomers, hence they cannot be mirror images of each other, and at the same time 3 and 4 are actually stereo isomers. They are not any other form of isomer. They don't show any other type of isomerism. So these 3 and 4 are geometrical isomers, and all geometrical isomers are diastereomers. Okay, let's look at another example. Here we have these three compounds, H, Br, CH, 3, H, Cl, CH, 3. Here we have HBr, CS3, and here at the back of the carbon we have, in the Newman projection, we have Cl and H, and the third one we have something like BrHCS3 here, and CH3H and Cl here. Okay, let us name them as 5, 6 and 7. So what is the relationship between the three? So if you see them closely, then actually for 5 and 6 you need to actually rotate this 7 in the same plane but 180 degree. Okay, so by rotation you will get something like HBr here and HCl here and CS3 here. So obviously you can see that 5 and 7 are identical. So 5 and 7 are identical. Okay, and you can so let us form the sawhorse projection for this Newman. So this is CH3, this would be H and Br, and for this you have to rotate the second carbon CS3 down, so you will have Cl, H and CS3 here. So you can see that 5 and 6 are actually diastereomers, and similarly 6 and 7 are diastereomers. So 5, 6 and 6, 7 are diastereomers. Okay, let us look at some more examples. We have here CS3, H, OH and ET, and another compound is ET, OH, H and CS3. Okay, so this is A and this is B. So let us make the sawhorse for this compound. So the sawhorse for this would be uh, so OH. If you see from actually, okay, so let us actually, why not have R and S configuration for sawhorse and for this fetch dash and for this sawhorse. So you know that this is the first in priority, this is the second, and this is the third. So this would be R and S, because the least priority group is on the dash of the wedge dash formula of this compound, so it will remain R. And in this case it will be, this is the first priority, this is the second priority, this is the third priority. So this is this is S origin, but the hydrogen atom or the least priority atom is on vertical or is on horizontal line, hence this would be R. S would convert itself into R. So both are actually R configured, hence A and B are identical. A and B are identical. Okay, let us look at fifth example. Here we have something like this: CS3H ethyl and CH2OH, and on the other hand we have something like CH2OH and CS3 ET and H. So what are these two compounds, A and B? A and B are neither stereoisomers nor enantiomers or diastereomers. Why? Because the number of carbon atoms here and here are not same, hence A and B are different. Different compounds. Okay, let us look at some more examples. So we have something like this: OH, H here, H here and OH here. Okay, so obviously 35 and 36, sorry, let us name them as A, B and C. So now you can see that the number of carbon atoms in this compound is 1 2 3 4 5, in this compound is 1 2 3 4 5 again. So what will happen is, you know that this compound is these two compounds are actually tautomers of this A compound, because there is alpha hydrogen here, and the removal of alpha hydrogen from this compound will actually convert this into tautomer of this enol. So this is a keto-enol group. So AB and AC are other, or you can say tautomers of each other. So what about now B and C? So B and C are geometrical isomers, and all geometrical isomers are diastereomers. Okay, so let us move on to the next topic, which is known as polarimeter tube. Polarimeter tube. polarimeter tube. Okay, so what happens is we have a tube, and this its length is, let's say its length is L, and we have certain compound filled in the uh, this tube, right? So obviously we are talking about the diastereomers, stereocenters and all those stuff. So obviously some carbon atom having chiral compound or chiral atom or chiral site is filled into this tube. Okay, so now what will happen is we have a light which is in all the directions. So we use a prism to convert this light into a plane polarized light. So let me make it big. So let's suppose we have this. Okay, let me draw it on this side. Let's suppose I have this light which is not a polarized light, it is in all directions. Okay, so we use a Nicol prism to convert this into a plane polarized light, or PPL, which is plane polarized light. Okay, so what will happen is, after this plane polarized light is passed into this tube, this polarized light can actually either sway in this direction or in this direction. If it sways in this direction, then it is called, if it sways in clockwise direction, then it is called plus D, which means dextro rotatory. And if it sways in anti-clockwise direction, then it is called minus L, which is called levorotatory. Okay, so we'll come into the polarimeter tube and what all calculations and formula we have about the rotations, the concentration of compound here, the length of the tube, the specific rotation which is caused by the compound, and length of the tube. We'll come into that a few minutes later. But before that, let us come into terms with some of the definitions of chiral compound, achiral compound, optically active compound, optically inactive compound. So we'll be looking into definitions of all of these in a short while. Okay, so what is a chiral compound? Chiral compound is simple definition, unsymmetrical compounds are chiral compounds. Okay, so chiral compounds are unsymmetrical compounds are chiral compounds. What is achiral compound? Achiral compounds are simple symmetrical compound. Okay, what are optically active compound? Optically active compounds are compounds which are capable to rotate plane polarized light are known as optically active compound. So capable to rotate plane polarized light. Okay, and what are optically inactive compound? or compounds, so they are incapable to rotate plane polarized light. So incapable to rotate plane polarized light. Okay, so now we will be looking into some of the formula we can derive from the polarimeter tube experiment. Okay, so let us look into that. So observed rotation is directly proportional to the concentration of the optically active compound in the tube, and it's also proportional to the length of the polarimeter tube. So observed rotation, which I signify it with alpha, is actually directly proportional to this symbol of directly proportional to the concentration of the compound and the length of the polarimeter tube. So alpha 0 will be equal to, at a particular source of light and at a particular temperature, into concentration of the compound into the length of the polarimeter tube. Hence, where this is the specific rotation constant, specific rotation. Hence, we can say that alpha at a particular source of light and temperature is equal to observed rotation divided by concentration into length of the polarimeter tube. And some of the units for this is alpha 0 is observed rotation. Observed rotation is measured via some instruments, and this value will be given to you when this type of question is asked, right? Concentration is gram per milliliter, gram per ml of the compound. Length is in decimeter. D is the source of light, and finally T is the temperature. Okay, so the definition of specific rotation can be written like something this: definition of specific rotation. So I can write definition of specific rotation something like this, that the rotation caused by 1 gram per ml of solution and 1 dm length of polarimeter tube at the given temperature and the source of light is called specific rotation. Okay, so rotation caused by 1 gram per ml of solution and 1 dm length of polarimeter tube at a given temperature and source of light. Okay, so with this we come to the end of this chapter, end of this lesson, and in the next video we'll be talking about the symmetry in a compound. So till then, good luck and goodbye.